This set of notes is for AQA core physics, and it's about specific heat capacity and examples of heat transfer. When looking at examples of heat transfer, we need to keep in mind the following key words. There appear to be quite a lot of them, however most of these words we should be quite familiar with from just general day-to-day usage. Any words that you're not familiar with, you need to sort of stop, make your own notes on them, and make sure you understand how to use all of these and have definitions of them written down in your own notes. If you need to refer back to this, you can always come back towards this page at any point in the tutorial. These keywords need to be used correctly in descriptive questions. Okay, the first main descriptive question is the vacuum flask. You're generally given a picture. It's a very common question, and usually it has a hot drink in the middle of it, although the same discussions can be used for something which is cold. If you look at the picture, it's giving us 4 key areas. There's a plastic cap or plastic lid. There's a partial vacuum between 2 walls, which could be either glass or metal. Those walls have shiny reflective surfaces both inside and outside. And although this one has a glass container to store the liquid in, as said earlier, that container could equally well be metal. So we would have to discuss this. We're going to discuss it on the principle that we've got a glass container. We will not make up anything. We should use only the phrases given to us in the question. Right, this is a typical long answer question of 6 marks. To get 2 marks, which is a sort of E stroke D type thing, you just need to write about 2 features. However, if you can then add another 2 to get 4, then immediately you're heading straight up into the sort of 6 mark category. In simple terms, a full, well-structured answer with most of the keywords that you see at the beginning will give you 6 marks. Simple statements on all 4 points in the picture will give you 3 stroke 4, and if you write about 2 or less points, then only 1 stroke 2, e.g. if all you did was write about back at the top. Right, so here's a typical answer. Right, plastic cap. If you could write all of this, then you're definitely heading towards sort of A category. Plastic is a poor conductor, or plastic is an insulator. It stops convection forming at the top of the flask, and so stops energy transfer by convection. It also stops particles evaporating from the liquid, and evaporation, as we're well aware, causes cooling. The plastic cap also stops conduction. If you've got those key points in, then you've pretty much got the idea. Generally speaking, no insulator is perfect, and we should really say reduces convection, reduces conduction, reduces evaporation. They tend to be a little bit flexible on that, and we can get away with the word stop, but if we can try and use the word reduces, it's much better. The glass container. Glass is a poor conductor, so reduces energy transfer by conduction. That's the key point there. The partial vacuum. As you'll see, some of these you can write more on than others. Right, a vacuum has a space with no particles in it. So in real life we can't do that. There's always a few particles, so the best is a partial vacuum. Hence, we can reduce conduction and convection currents within the wall because we've got less particles. So the vacuum reduces energy transfer by conduction and convection. Silvered surfaces, these reflect infrared radiation. So if the liquid is hot inside, it reflects the infrared radiation back towards the liquid, thus stopping it cooling as quickly. So silvered surfaces stop or reduce energy transfer by radiation. Okay, so if you've got all of those points in that level of detail, you've got 6 out of 6. As you reduce the amount of information you have on each point, then your marks go down. It's pretty much effort. If you learn this, it's a very good question. It keeps coming up, and questions like it keep coming up. So the idea is that you're using all the key words that we saw at the beginning of the tutorial. Those are the words in bold. Right, another classic one is cooling and surface area, and we've got an example of an Arctic fox and a desert fox, but equally well it could be elephants with their big ears and things like that. So an Arctic fox has small ears. How does that help it keep warm in a cool, cold environment? Well, pause the video and have a little think for yourselves, but here is the answer now. Okay, if we look at the picture, we see that the Arctic fox has extremely small ears. Those ears have a small surface area. That's important. That means they reduce energy by radiation from the fox. That's it. Okay, 2 marks. Each mark 1 point. It's very specific, so you have to get this answer almost perfect. Small surface area, reducing radiated energy transfer from the fox. Okay. The next one, how large is on a desert fox, help keep the fox cooler in a hot environment. Well, here's a cute picture. There's our desert fox. As you can see, it has huge ears compared to the little Arctic fox. So how does that work? Okay, pause the video again and have a think. Here's the answer. The ears have a large surface area, so increasing the radiated energy transferred from the fox. So it's the complete opposite of the previous one. So if you know one answer, by comparison you can then work out the other. But you do need to make sure again that you know what's being looked for in these questions. Both of these are 2-mark questions. You're only likely to get 1 in an exam. Just repeating the opposite isn't really going to gain you any marks. So make sure you've got that in your head, and it could equally well be other animals or other situations. Right, moving on now. Specific heat capacity. This is quite a big chunk, and there's usually at least one question on this, and it's an equation question, really. The equation is going to be given to you in the exam on an equation sheet, and it will be in the form of words: energy transferred equals mass times specific heat capacity times temperature change, and in the form of letters: E equals m times c times theta. You need to be familiar with both. The units are not given, so you must make sure you understand the basic units. Energy is in joules, mass in kilograms. Theta, which is temperature change, is in degrees C, and specific heat capacity, which is as an odd unit, is joules per kilogram degrees C. What does specific heat capacity mean? Well, it means the energy needed to raise 1 kilogram of a material by 1 degree C. The example I've given is aluminium, which has a specific heat capacity of 900 joules per kilogram degrees C. So that means you need 900 joules to increase the temperature of a 1 kilogram block of aluminium by 1 degree C. And so on. So a 1 kilogram block by 2 degrees C would need 1800 joules. Okay. As I said before, you don't need to learn the equation, it's on a formula sheet. You do need to know the units, so they do need learning. Right, if we're using this equation, we tend sometimes just to have the E equals m times c times theta version, which is fine, no rearranging there. You can write that equation out and then put the numbers in the correct sequence. But occasionally they might ask you to be working out the specific heat capacity, or the mass, or theta, and so we have our formula triangle. This will appear a lot in various tutorials, and you should be able to use it and therefore rearrange equations with great ease. So, to cover the E, we see that we get m times c times theta, just to convince ourselves that we've got the formula right and the triangle correct. Right, if we want to get c, we cover the c and we have E divided by m times theta. It's important to put them in brackets because the E is divided by both m and theta. It can be quite a common mistake not to put them in brackets, so make sure you put the m and theta in brackets. Right, if we want m, we cover the m and we get E equals c times theta. Again, put them in brackets because we're dividing E by both of the numbers. And theta, the temperature difference, is E over m times c. So if you answer questions, if you write the formula triangle down, when you know it's a specific heat capacity question, then what you can find is you can rearrange them easily enough. Right, some examples. Just work your way through these examples. You'll see the first one is a classic example, which is just E equals m times c times theta. Notice we've got a start temperature and a final temperature. So theta being the temperature difference, is 35 minus 50, which is 20. Other than that, we're just putting the numbers in the right order. You notice as well that the energy is actually a very big one, 4 1,200,000, which can be written as 4,200 kilojoules. B familiar with the kilo, which means 1,000, or in this case 4.2 megajoules, capital M being mega, which stands for million. Both of those letters will be used throughout the course, so you need to be familiar with K and M and mega. Right, B, looking at water and we're finding the mass. Well, again, we can go back to a formula triangle. We get E equals M equals E over C times theta. We put the numbers in. We've got 5,600 joules. So we add an extra 3 zeros. We have to be working in standard units, and the standard unit of energy is the joule. So it's 5,600,000. We have 4,200 as the value for the specific heat capacity, and the temperature difference is 32 minus 25, which is 7. When we put those numbers in, we get 190 kilograms. It's likely that it will only be 1 mark, and that if you miss the kilograms you may well lose the mark. So just be careful, make sure you learn your units. So make sure you're familiar with these and follow it through, and if you need to review the triangle, go back and have a look at that. Now it's your turn. Let's have a go at the following questions. So question 1. These are relatively straightforward, so what you should do is just pause the video, write the answers down with full working out on a piece of paper, and then just check the solutions with the answers as they come up. So if you pause the video now. Right, okay. If you just now watch the rest of the video, we'll put the solutions on the screen for you. So question 1, this is fairly straightforward, it's just about energy. So we just use the equation from the formula sheet without any rearrangement. We should always write the equation down, even though it's given to us, just because we should always have the full answer and just get into good habits. So E equals M times C times theta. Putting the numbers in the correct order gives us 0.5 times 490 times 20, which gives us the answer of 4,900 joules. There's no need to really change that unless of course they're asking, in which case it could be 4.9 kilojoules. But tend not to do anything with the numbers, just leave them as they are. They come off the calculator and just write them out like that. You don't want to make any mistakes through miscopying. Right, question 2. Again, it's fairly straightforward. It's just talking about the energy needed to raise the temperature of the block of aluminium. A little bit trickier this time because we have to work out theta, but it's not too difficult. It's 50 minus 20, which is 30 degrees C. So putting the numbers in the correct order gives us an answer of 5,400 joules. So fairly straightforward, no rearrangement. The equation straight off the formula sheet and the numbers straight from the questions. Just make sure you know what theta is, i.e. the temperature difference. Right, it's a little bit hard now, going up to grade B stroke A. Having said that, certainly question 3 could turn up on a core paper. It's certainly at the top end of the grade C. So bottom end B, top end of C. So what's the specific heat capacity of aluminium wood? Obviously you need to get your formula triangle and rearrange that. So again, pause the video, give yourself a few minutes to write out the solutions, and then check the answers. So pause. Okay, here's the solutions. Right, we rearrange it, and from the previous slide we see the C equals E over M times theta. We look at the data and see we've got 36 kilojoules, which is 36,000. Put 3 zeros in. That's a common thing that we need to do to change kilojoules into joules. We then divide it by the mass of 5 times 8, because theta is the temperature difference, which is 22 minus 14. And when we work all that out, we get 900 joules per kilogram degrees. Okay, fairly straightforward. It could be worth showing theta equals 22 minus 14, however, no, it's there anyway. Alright, question 4, a concrete wall question. Receiving a lot of energy, 13,200 kilojoules. Starts at 15 degrees C and its specific heat capacity is 850 joules per kilogram degrees C, and the mass of the wall 6,000 kilograms. We can't get the final temperature directly, we can only work out theta, the temperature difference. So we start with that, and we find that when we put the numbers in and get rid of the K, our 3 zeros, in the front of 13,200. We get an answer of theta is 3 degrees Celsius. That's the temperature difference. So we know we started at 15, so therefore the final temperature is 15 plus 3, which is 18 degrees C. That would not be given, that final little equation is not given to you in any exam sheet. You've got to be able to know that theta is the difference between the two temperatures, start temperature and final temperature, and so therefore in this case 15 plus 3 is 18 degrees C. So that's definitely trending up towards a grade A question, but with a little bit of thought it should make some sort of sense. Okay, right, we now move on. We've started going with the last three little sections, U values. Now, these are an odd little thing in our syllabus, and effectively you just need to learn what they are and how to answer the questions. So, to 2 mark the U value, a method of comparing the insulating properties of different materials, and the lower the U value, the more effective the material is as an insulator. Learn that. Too easy now. Okay, no descriptions, nothing. Just make sure you understand that. There's quite a lot of learning in this particular section of work. There's no easy way around it. The more time you put into it, the more you'll get out of it. An example that's a little bit harder than that, could be a sort of grade B, a bit higher tier, is using some, what's called a quantitative argument where there's a number put in. Now they're not going to ask you about actual values of U values, but what they will do is say something has a higher U value than another. So, typical question, normal glass has a U value which is twice that of E glass. The higher the U value, the more something is as a conductor. So that means normal glass is twice as effective at conducting energy than E is, or normal glass is an insulator. Don't get confused by this. It's the lower the U value, the better. So normal glass is a worse conductor. Right, so the answer, thinking in terms of insulation. So the best insulator is E-glass because it has a lower U value, 1 mark. It's 2 times more effective than normal glass as an insulator, 1 mark. You could go for the converse argument, which is that the worst insulator is normal glass because it has a higher U value and it is 2 times more conductive than E-glass. So either way it's fine. Easy to get confused, just remember the lower the U value, the better the material is. Right, moving on. Payback time. Quite common, and you may well have to think about this in your future lives. We have a solar panel to heat water, or solar water heating panel as it's known as. You should be able to describe how this works. So for instance, infrared radiation passes through the transparent top and is absorbed by the black pipes, black being the best absorber of infrared radiation. The pipes are made of metal, which conducts heat, so therefore cold water comes in and is heated by the metal pipes, and warm water goes out. So some sort of idea there of infrared radiation, good absorbers of infrared radiation, and conduction of heat through metal pipes. Anyway, that's a little aside. The main thing is talking about solar water heating panels and whether they're cost effective. So they cost 5,000 to buy, and you save £200 a year. So the payback time is 25 years. Fairly simple maths. That will be a grade C. Is it a good investment? Well, as long as you can discuss this with reference to the numbers and make sense, then any sensible answer will be accepted. So here's my views on this. A good investment? No, it's not a good investment because it takes 25 years to get your money back, and in that time I may well have moved house, so therefore I won't get my money back from the 5,000 investment. Okay, there we go. Seems to make some sort of sense. Is it a good investment? Yes, I believe it's a good investment because it helps reduce my electricity bill for heating water, or my gas bill for heating water, so I'm not therefore using fuels that produce extra CO2, which will add to global warming and thus heat the earth, and I feel that it may well add to the value of my house because of this. So there we go, two sort of arguments, both referring to some level of theory. Okay, so as long as you can put some theory in and look at the numbers, then no one can really fault your argument. Right, house insulation. Look at the diagram, it just shows where the main forms of heat loss are. The numbers in brackets are what you can reduce it to if you use insulation. You should be able to discuss house insulation and how they work using the words, the keywords that we had at the beginning of the session, and any of these 6 features. Again, this is a good long answer question, just like the first one on the vacuum flask, and if you could use these and discuss around the keywords how they work. So as an example, loft insulation, typically made of glass fibre layers. Glass fibre traps pockets of air. Air is a very good insulator, and so heat loss due to conduction is reduced. If we put a layer of silver foil around that insulation, that reflects infrared radiation back into the house and also reduces heat loss due to radiation, therefore keeping the house warmer. Double glazing is a partial vacuum, less particles, so reduces heat loss due to conduction. You can get special glass which reflects infrared radiation back into the house as well. And we'll just jump down to carpets. Carpets are an insulator which reduces heat loss due to conduction. So those are the sort of things that you should be able to discuss, and in that level of detail, and again that would be looking at getting 4 marks in that particular type of question. So there we go, that's this topic finished. So make sure you're quite familiar with using specific heat capacity equations and descriptive answers, and using all the keywords that are at the beginning of the video, and also, as you can see in the brackets here at the end of the video, they're very important and they can come up different questions. Okay. Alright, we'll move on to the next tutorial, and I hope this has proved useful to you.